In our first lecture, we made a brief introduction to circuit theory. In fact, we started our introduction to circuit theory. Today we're gonna continue. And in our introduction, we talked about basic definitions like charge, current, voltage, power, and passive sign convention, which are quite important for circuit theory. Today, let's first quickly remember what those were, okay? And then after that, very short summary, we will talk about Kirchhoff's laws, okay? Kirchhoff's current law and Kirchhoff's voltage law, what they are. We will define as we go along, and if time permits, we will also be talking about the so-called terminal equations. Okay. We start with the definition of charge, which is a conserved property of subatomic particles, we say, which is which lies in the very root of the phenomenon called electricity. And then once you have charge, and once the charges are moving, then you have the current. Okay. And then suppose, for instance, this is some component in your circuit. Okay. A resistor, a voltage source, a capacitor. We'll define all those as we go along. But it doesn't matter what component this is. Suppose it's your component, and then the rate of change of the flow rate of the charge through a given area. In this case, the area would be the cross section of that wire, is what we're calling the current. Okay, for instance, for this component, given the direction, we will measure some charge moving, and that gives us the current. Okay, and then we also talked about voltage. What voltage was? Given voltage was the potential energy, or the potential energy difference between two given points for a given polarity. Okay. And suppose the polarity is given as such, and then that allows us to talk about voltage. Okay. And then we talked about the passive sign convention. Note that the polarity of the voltage and the direction of the current is arbitrary, meaning that we choose the direction of the current, and also we choose the polarity of the voltage. Okay. And then there's a passive sign convention we talked about in our first lecture, which relates the two, the direction of the current and the polarity of the voltage. Okay. And the passive sign convention was such that if, for instance, you choose the polarity of the voltage first, plus minus, and then when you choose the current for that component, okay, so let's call it X, component X, then what you do is you choose the direction such that it enters from the positive label terminal and leaves from the negative label terminal. Okay, or suppose that you choose, suppose it's the same component, you choose the direction of the current as such, okay, from this terminal to the top terminal, and then if you want to obey the passive sign convention, you should choose the polarity of the voltage such that here you have plus and here you have minus. Okay, this is VT, and this is called passive sign convention. Now, the power okay, let's concentrate on this choice. The power of the component X, we said in our first lecture, equals the product of voltage that appears across its terminals times the current passing through it. Okay, therefore in this case P of t equals IT times VT. Okay, this is measured in amps, voltage is measured in volts, and power is is measured in watts or joule per second. Okay, and one benefit of sticking to the passive sign convention is that if you do that by looking at the sign of the power, we can determine whether this component is providing energy to the circuit that is part of, or it's absorbing energy from the circuit. Okay? And the relation was as follows: if PT is positive, okay, if the power obeying passive sign convention is positive, then it means your component, which we denote by X, is absorbing power. Example, a heater, okay? A common resistance. The other possibility is that power turns out to be negative, okay? And if power is negative, then it means your component is delivering power to the circuit that it's part of. For instance, the battery in your smartphone, if it's not being charged, it is delivering power to the gadget. Okay, so those were the important things from our first lecture, and today we'll be talking about some other important things. Now, in this course, the main goal is to solve a circuit. Okay, and what is solving a circuit? By solving a circuit, generally, we will mean, given a circuit, figuring out all the associated currents and voltages of all the components that make up our circuit. Okay, for instance, if you have a circuit that's made up of 5 two-terminal components, okay, so that makes 5 voltages, V1, V2, V3, V4, V5, and 5 currents, and a total of 10 unknowns, 5 voltages and 5 currents. So to solve that particular circuit, you need to figure out those 10 unknowns. And to figure out those 10 unknowns, you need 10 equations. Okay? Now, some of those equations, in fact, exactly half of those equations, at least for LTI resistive circuits, will be coming from the so-called network equations or network laws. Okay? They are Kirchhoff's, namely the Kirchhoff's current law and Kirchhoff's voltage law. And the remaining half, or LTI resistive circuits at least, will be coming from the so-called terminal equations. And in today's lecture, we'll be talking about those two things. Okay? Now, let's begin with Kirchhoff's laws. First is Kirchhoff's current law. Okay. We will generally use the abbreviation KCL whenever we mean Kirchhoff's current law. And that law is a direct implication of our assumption. Remember that we made 2 assumptions in our first lecture when we were dealing with circuits, and those assumptions were, one of them was that the circuit is a lumped circuit, okay, meaning that more formally, electrical effects happen instantaneously. And the second assumption, which we call A2, was that the net charge inside any closed surface is always 0. And this second assumption is what's giving us KCL, Kirchhoff's current law. Net charge inside any closed surface is always 0. Okay, so that was our second assumption. And that assumption immediately brings Kirchhoff's current law, KC, which is, well, you can express it in many different ways, but they're the only equivalent for any closed surface, okay, regarding your circuit, or you can even consider it more general. The sum of incoming currents equals the sum of outgoing currents. Okay? And what's incoming and what's outgoing, we determine by looking at the direction of the currents. So let's illustrate what that definition or rule is saying. Okay, here's an example. Okay. Consider some closed surface, okay, possibly associated to our circuit. And associated to this closed surface, we have, let's say, 4 currents, okay, or 4 wires, let's say, is entering or leaving this surface. Okay. Here we have I1 going into the surface. Here we have I2, here we have I3, and here we have the 4th and the last current, I4. Okay, what's incoming and what's outgoing? These I1 and I2 for this surface are incoming because they are entering into the surface, and I3 and I4, they are leaving the surface. Therefore, they are what we're calling outgoing currents in this law. Okay. Now let's apply Kirchhoff's current law to that particular situation and figure out a relation between those 4 currents. Okay. The incoming currents are I1 and I2. And outgoing currents are I3 and I4. And KCL says that sum of incoming currents must equal sum of outgoing currents. Okay? And this law applied to this particular situation immediately gives us I1 plus I2, sum of incoming currents, must equal I3 plus I4. Okay. Remember that the direction of the current is something that we choose. In a sense, it's arbitrary. Okay. Therefore, this situation can be equally well represented by this picture. Okay, this is S. We have this is that, this wire, this, and so on. Okay, and now since the direction is arbitrary, we can make all the currents as incoming. Okay. So here we have I1, it's already incoming. Here we have I2, it's already incoming. We don't have to do anything. And here we have I3, it's outgoing, but we want it to be incoming. Okay. Now clearly, if you swap this, the direction of the current, you cannot leave I3 as it is. Okay, then nothing makes sense in that case. If you swap the direction, you have to negate the current that you're computing, or that you're going to compute, or you're measuring. Okay. Likewise, here we have I4 going out, and then we want that to be an incoming current. We change the direction of the current and we have to negate it. okay, minus I4. Note that in this situation, all the currents now are pointing into the surface. Therefore, we can again apply Kirchhoff's current law, and hopefully we will obtain the same relation that you obtained in the first case. Otherwise, this law wouldn't be a law at all. Okay? So now we have incoming currents are I1, I2, minus I3, and minus I4. How about outgoing? We have no outgoing currents. Okay? So KCL now implies the sum of incoming currents I1 plus I2 plus minus I3 plus minus I4 must equal sum of outgoing currents. We have no outgoing current. That means the sum is 0. And this is the relation between those four currents. Note that this equation here is just another way of writing down this equation. Here's another more circuit-like example. Okay. Suppose that we have some circuit with a bunch of components or elements. Okay. We have 1, 2, 3, 4, 5 components connected in this way to make this circuit. Okay. And here we have a node. Suppose that this current is I1, this current is I2, and this current here is I3. Now we can find a relation between those three currents if we consider our so-called closed surface, the imaginary box that contains that node where those three terminals meet. Okay. Now, to this surface or to this node, we have associated to that surface, we have three currents, I1, I2, and I3. I1 and I2, they are entering to the surface or to the node, and I3 is leaving the surface or leaving the node, and by KCL, the sum of incoming currents must equal the sum of outgoing currents. In this case, we have only one outgoing current, therefore I1 plus I2 must equal I3. Note that when writing this equation, we didn't need to know what type of component this is, whether it's a resistor, a current source, a voltage source, a capacitor. We don't care, okay? Because KCL, likewise KVL, which we will see soon, only cares about the interconnection, that is, which component is connected to what component. And it doesn't care about the internal dynamics, okay, internal gears of that particular component. That's why it's called Kirchhoff's current law and Kirchhoff's voltage law is called the network laws, okay, sometimes. Now let's move on to the sister law, that is Kirchhoff's voltage law. Okay. And as some of you will rightly guess, it will be a law based on voltages, and also it will only care about interconnection. It will not care about, like Kirchhoff's current law, it will not care about the particular component or the type of components. Okay, Kirchhoff's voltage law. Okay. And the abbreviation that we frequently use is KVL. And this, okay, KCL came from the second assumption, which was net charge of any closed surface is 0 at all times. And Kirchhoff's voltage law is coming from the path independence of the voltage. Okay, so the voltage is determined only by the endpoints of any path. Okay, it doesn't care about what path connects those 2 points. A direct implication of path independence for the potential energy difference between 2 points. And here is the law. Sum of voltages along any loop, and loop is any closed path. Okay. Any loop closed path is 0. Okay. Example. Suppose that this is our path, okay, with some points labeled A, B, C, D, and E, let's say. C, B, A. Okay? Some path, let's say in some electric field. Okay? And now consider the path or the loop where we start from A. From A we go to B, from B we go to C, from C we go to D, from D we go to E, and from E we return to where we started from. Okay? Note that associated with the loop there's also a direction, and our direction in this case is clockwise. Okay. Now KVL says that, okay, follow this loop, and as you go along the loop, just write down the voltages that you encounter. Okay, we start from A, and then first we move from A to B. So the first voltage is AB, and then from B we move to C. So the next associated voltage is BBC. From C we move to D. Okay, voltage associated with VCD. From D we move to E, and so on. Finally, from E we return to our starting point, EEA. Okay. Now this is the loop, closed path, and this is the sum of voltages that we come across, okay, as we go along the loop. Now since the voltage is path independent, okay, and our path is closed, therefore we start and end at A. Therefore this sum of voltages must equal the voltage or the work done by the unit charge when you start from A and end up at A. Since it's path independent, if you do just nothing, you start at A and you end at A, you achieve your goal, and you achieve your goal without doing anything, okay, because you start and end at the same point. So clearly this voltage is 0, VAA. But due to path independence, this voltage must equal the sum of all those 5 voltages. Therefore, sum of all those 5 voltages must equal 0. Okay, and that's KVL. Likewise, okay, we could have gone in the other direction. Okay, we start from A again, and then first we move to E, then D, then C, then B, and finally end up at A. So that will give us VAE plus VED plus VBC plus VCB plus VBA. Okay, so that's another loop, and these are the voltages that we come across along the loop. And once again, by KVL, their sum must equal 0. Or you can write some other variations. Suppose that we want to go from A to C. Okay. This is an indirect implication of KVL. From A to C, you can go through B. Okay. From first A to B, then from B to C. So that gives you BAB plus BBC. Since path is independent, you can reach C also from that direction. First to E, then to D, then to C. BAE plus BED plus BDC. Okay? Since start and end points AC are equal, that means these sum must equal, this sum must equal that sum of voltages. That's also another way of writing KVL. And so, now let's give another example. Suppose this is our circuit. Once again, KVL, like KCL, only cares about interconnection. So in order to be able to write equations coming from KVL, we don't have to know what these components are, whether they're resistors, capacitors, sources, and things like that. Okay, in this circuit, suppose we're interested in the relation between the following four voltages. Plus, minus, V1. This is the voltage of this component with polarity plus, minus, as given. And then we have the voltage between this point and that point with polarity plus, minus, and that's called V2. And then we have the voltage of this component with polarity plus, minus, given that, V3. And suppose that the voltage of this component with polarity plus, minus, given such, is called V4. Okay. Now, consider this loop, okay, clockwise, and it visits all those four voltages, V1, V2, V3, and V4. Okay. Now let's apply KVL and find the relation between those four voltages, because to be able to apply KVL, all you need is a loop, a closed path, and we have that closed path. Okay. Now we have to be careful about one thing, because the definition of KVL was not the precise. Okay, now I'm making it precise as follows. As you go along the loop, okay, you encounter certain voltages, okay, and then all those voltages, in order for you to be able to apply KVL, must have the same polarity orientation with respect to the loop direction. Okay, for instance, here, suppose that we start from this point and then, okay, next stop is this point, and then we have this node and finally that node. From this node to that node, the associated voltage has polarity plus, minus. So if that is our polarity, okay, that we're going to stick to, all the other voltages must have the same polarity, plus, minus, plus, minus, plus, minus, plus, minus, so that the sum of those voltages equal to 0 makes sense, so that we can apply KVL. Okay. So we start from this point. The first voltage is V1, okay, and it's plus, minus. All the other voltages must also be plus, minus. And then we have V2 plus, minus. Okay, we're going in clockwise direction. Everything is fine. And then we have V3, but we cannot direct write V3 because V3 doesn't go plus, minus. It's minus, plus. Okay. So it doesn't fit to choice of polarity, but that's just a minor difficulty because we know that polarity is in a sense arbitrary. You can always swap the polarity. If minus plus doesn't make us happy, we can always make it plus minus. But of course, if you swap the polarity, you have to negate the voltage. This and that, they're saying the same thing. But this is better for formal reasons only. This is better because it coincides with our polarity choice, plus minus, okay? So plus minus V3. And also we have here minus plus, but we want plus minus as we go along the loop. Again, we swap the polarity and negate the voltage. Plus minus V4 equals 0. Okay. Therefore, KVL says that those four voltages must satisfy this relation, which can be written as V1 plus V2 must equal V3 plus V4. Okay. So let's apply it to a numerical case. Let's use this relation to obtain something. Let V1 V2 cosine 10t plus 45 degrees volt. Suppose that we measure this V2 or compute V2 as 12 volts, a constant voltage. And suppose we have V3t measured or computed as 5 sine 5t volts. Okay, 3 voltages. Suppose we already know somehow those 3 voltages. And we are also interested in figuring out what V4 is. We don't have to do a measurement to figure out V4 because those 4 voltages, they make a loop and we can always use KVL to compute the remaining voltage. Okay? So by KVL, we know that V4 of t depends on the remaining 3 voltages as follows. V1 of t plus V2 of t minus V3 of t. Okay. I just rewrote this equation here in its new form. Okay. Therefore, V4 of t, if you already know the voltages on the right hand side, can be written as 12 plus 2 cosine 10t plus pi over 4 minus 5 sine 5t volts. Okay? Never forget writing down the units. Okay. So that's all there is to KCL and KVL. In our next lecture, we will continue with terminal equations.